Hello students, welcome back. Today's topic is energy band gap and light emission in semiconductors. So we try to understand a little bit about energy band gap and how is it related with respect to light emission. So this particular graph shows us the electron energy with respect to space coordinate system. So you can very clearly observe the valence band and then the conduction bands. Well, let's try to imagine that there is a electron which is present here on top of the valence band. Since it is in the valence band, we say that it is in rest position. Now suppose if this electron is being supplied with a potential or with an external voltage, then it gets energized. Now when this particular electron gets energized, it jumps into the conduction band. So we call it as flow of the electron. Now with respect to semiconductors, whenever any electron jumps into the conduction band, we say that parallelly there will be a hole also getting created. So this we call it as electron hole pair generation. Now the physics says that the excited electron cannot stay in the conduction band always. So after some time it has to jump back to its rest position, which is in the valence band. So when it falls back or when it jumps back from the conduction band into the valence band, we call this process as recombination, because the electron combines with a hole. So this is called as recombination. So during the recombination process, the electron which had initially acquired the energy, say for example, if this is the energy E that was acquired by the electron during the electron hole generation phase. Now during the recombination phase, the same electron, when it jumps back, it has to release the energy. Now this energy that is being released is either in the form of heat or in the form of light. Okay, so now the question is whether all semiconductors emit heat or whether all semiconductors emit light. So let us look for the answer. So the point is, if we want light emission, then it is directly related to the semiconductor's band gap energy. We usually denote the band gap energy as Eg. So let us try to understand. Well, there is a very simple relation between the energy band gap of a particular semiconductor with that of the wavelength of the light that is being emitted. Okay, so which is Eg is equal to Hc upon lambda. So here Eg stands for the band gap energy of a particular semiconductor material. H stands for Planck's constant. H stands for Planck's constant. Usually its value is 6.626 into 10 raised to minus 34 joules. Then what about C? C is the velocity of light. So when we say light, it means velocity of the photon particle, which is usually 3 into 10 raised to 8 meter per second, and lambda is the wavelength of the photon that is being emitted. Right. So on a simple note, it can be understood that higher the energy band gap, lower will be the wavelength of the photon that is being emitted. and lesser the energy band gap, higher will be the wavelength of the photon that is being emitted. So this we can very clearly understand with respect to the electromagnetic spectrum. So the question that arises is, do all semiconductors emit light after electron-hole recombination? Well, the answer is no. We'll try to understand by considering the example of silicon. Well, silicon is a very popular semiconductor, and we know that almost all the rectifier diodes are made up of silicon. Electron in the silicon crystal, when it is energized, it jumps into the higher energy level. Now after some time it has to jump back to its original place. When doing so, whatever energy it had acquired, the same energy has to be emitted back. Okay, so during the course of this energy emission in silicon material, whether the energy is it emitted in the form of light or in the form of heat. Okay, so let's try to understand it. So we know that Eg is equal to Hc upon lambda. Now because Eg is 1.1 electron volt, so let us try to find the wavelength of the energy that is being released. So lambda can be written as Hc upon Eg. So H is 6.626 into 10 raised to minus 34 joules second, and C, which is velocity of light, is 3 into 10 raised to 8 meter per second. Eg, which is 1.1 into 1.6 into 10 raised to minus 19 joules. For a silicon, the band gap energy is around 1.1 electron volts. The energy when it is released, when electron and hole do get recombined, the wavelength will be 1130 nanometers. Now similarly, if we do it for gallium arsenide, wherein the band gap is around 1.43 electron volts, what will be the lambda? Okay, so what is the lambda for gallium arsenide? Similarly, when we are using the compound semiconductor gallium arsenide phosphide with a band gap of 1.9 electron volt, what will be its lambda? Okay, so this, when substituted, we get some calculated values, right? Okay, so let us just look at those calculated values. Okay, so this is for gallium arsenide phosphide. So for both the things, what will be the value of lambda when it is calculated? So for gallium arsenide with a band gap of 1.43 electron volt, the wavelength with which the energy is being released is around 869 nanometers. Similarly, for gallium arsenide phosphide, wherein the band gap energy is 1.9 electron volt, the wavelength of the energy that is being emitted is around 654 nanometer. And for a silicon, it was anyhow 1130 nanometers. So based upon these three values, what are we supposed to infer or understand? Well, if we just go back and look at the electromagnetic spectrum. So Left hand side, this is increasing energy, which means the frequency is increasing. Similarly, towards the right hand side, the wavelength increases. Okay, so this is the entire electromagnetic spectrum. Now if we just look at only the visible light that human eye can see or is sensitive is very small. So the range for visible spectrum is only this much. Now if you want to say it in terms of wavelength, that too in terms of nanometers, it is roughly around 350 nanometers to around 750 nanometers. Okay, so roughly the spectrum is around 400 nanometers. Okay, so that's it. This is what the human eye is capable of seeing. Beyond that, we cannot just see the light. Okay, so now that means, where does silicon material fall with a wavelength of around 1130 nanometers? Does it fall within the visible light spectrum? The answer is no. So the silicon wavelength, the energy of the wavelength that is being emitted by silicon atom is 1130 nanometers. Okay, so what about gallium arsenide? Well, gallium arsenide, its value is roughly around 930 nanometers or 969 nanometers. Okay, so which means this also doesn't fall under visible light spectrum. So what does it mean? Can't we not use gallium arsenide material for making or for fabrication of LEDs? The answer is yes, we can use it. However, the light that is being emitted is not within the visible light. It falls under the infrared range. Okay, so it is for this reason that we usually call them as IR LEDs. Okay, so that is gallium arsenide material based LEDs are normally called as IR LEDs because the wavelength that they emit are in the infrared region. Now what about gallium arsenide phosphide? Okay, so this is well within the visible light spectrum. Okay, and its range was somewhere here around 690 nanometers, which means the light that is being emitted by gallium arsenide phosphide LED material is usually red in color. Okay, because its wavelength is somewhere here. Okay, so that means finally, now coming to the nature of the emission, if the semiconductor material is of silicon, the wavelength that is being emitted is not within the electromagnetic light visible spectrum. Okay, so we see that instead of photons, here phonons are emitted. Phonons are just the packets of heat energy. Similarly, if it is gallium arsenide, then photons are emitted but they are in infrared region. But if it is gallium arsenide phosphide, then the photons in red visible region are emitted. So that means we can call it as a red LED. Okay, so similarly, if we can properly tune the wavelength of the light that is being emitted in different values within the visible spectrum, then we can get different colored LEDs. Okay, so finally the answer is that not all semiconductors emit light after electron-hole recombination. It is only the semiconductors that have the capability of emitting energy whose wavelength falls within the visible spectrum are capable of emitting light. Okay, so I think the concept is clear. Thank you.